and I'm delighted to welcome you to the session today, where we'll be exploring ways in which machine learning is going to be transforming science. Before getting started with the session, I'm delighted to announce that this year, CCAIM, the Cambridge Centre for AI and Medicine, will be hosting its annual AI and Machine Learning Summer School. This is for data scientists, students, academics, and industry experts with AI and machine learning backgrounds. And it's going to cover a wider range of topics, from large language models to data-centric AI to causal deep learning and much more. And this is going to be taking place from the 2nd to the 6th of September later this year. If you're interested in learning more, sign-ups are now open, so you can scan the QR code now. So I'll just leave it on the slide for a few more seconds, and you can find out more details. And if you miss the QR code now for whatever reason, you can find more details on our lab's website and sign up. And we'll be releasing more details of the schedule and making a lot of really exciting announcements about the summer school over the coming weeks in the lead up to the event. So do sign up now and make sure not to miss out. Back to today's session, I'm delighted to be welcoming one of the PhD students from our lab, Krzysztof, who's going to talk about two of his recent pieces of work, time view and shape arithmetic expressions, in today's session. In the second part, we'll then move to our panel discussion, where I'm delighted to welcome three distinguished guests from industry, who I'll introduce more formally later on during the session when we move to our roundtable discussion. So now, without any further ado, I'd like to pass over to Krzysztof for his talks.
Okay, so hi everyone, my name is Krzysztof, and today I would like to present two recent papers published by our lab. And I'll start with one entitled Shape Arithmetic Expressions, Advancing Scientific Discovery Beyond Closed Form Equations, authored by me and Michaela. And this paper is going to be presented at AISTATS 2024. So before I go into more details, I first would like to introduce you to this very exciting area of symbolic regression, which is a very important area of machine learning. So symbolic regression aims to fit closed form expressions to data, where a closed form expression is a type of mathematical expression, which is a combination of variables, arithmetic operations, such as addition, subtraction, multiplication, division, some well-known functions, such as trigonometric functions, exponential or logarithms, and numeric constants. And such equations, if concise, are interpretable and well suited to mathematical analysis. And this is exactly these properties that led to a widespread adoption of symbolic regression in areas spanning from risk scoring in medicine to physics to material science and even to biology. And actually, in fact, our lab has recently done a lot of work on symbolic regression, from new optimization algorithms to their applications in discovering differential equations. And I invite you to check out these papers as well. So what we observed is that symbolic regression excels in settings where the ground truth is a closed form expressions. However, its effectiveness becomes less certain when it is applied to scenarios with no underlying closed form expressions. And some phenomena do not have a closed form expressions. For instance, if you look at the trajectory of a nonlinear pendulum, or some functions from physics are determined experimentally rather than derived from theory. For instance, current voltage curves or drag coefficient as a function of Reynolds number. And it's becoming even more relevant in life sciences, where the complexity of the studied phenomena makes it more difficult to construct theoretical models. So we claim that symbolic regression may struggle to find compact expressions for certain relatively simple functions. And as an example, we tried to fit a symbolic regression model to a data set of stress strain curves. And as you can see, these functions are relatively simple, consisting of a few well-defined segments. However, when we try to fit symbolic regression to it, we can see that they found expressions either fit very poorly or they become very complex, and thus their utility is diminished. So to address this problem, we turn our attention to a well-known flexible models called generalized additive models. And here the target variable y, or more generally the function of y, is described as a sum of univariate functions called shape functions, each taking a different feature. And they're usually considered transparent, as each shape function can be visualized as a line plot, and it acts independently of the other shape functions. They can also be extended to include pairwise interactions, and then they can be visualized using 2D heat maps. So the main disadvantage of GAMS, though, is their inability to model more complicated interactions. For instance, if we have three variables, x, y, and z, then x times y divided by z cannot be really captured by generalized additive models or GAMS. And this is exactly what we demonstrate in the next experiment. So we chose a few simple equations from the Feynman symbolic regression database, and we compared the performance of GAMS with interactions, and a black box model in XGBoost in that case. And we can see that the performance of GAMS is much more lower than the performance of a full capacity model, and the gap between GAMS and XGBoost is only partially closed by adding pairwise interactions. And it's also important to note that interpreting this GAMS with interaction is more challenging because we have to interpret this to the heat maps, and the individual shape functions cannot be analyzed independently because they may depend on the same variable. So to address these limitations of both GAMS and symbolic regression, we introduce a new type of machine learning model that connects symbolic regression's ability to model complex interactions and GAMS' power of efficiently describing univariate functions by plots. So we call this family of models shape arithmetic expressions, or Schaars, and they can be defined similarly to closed form expressions, but instead of allowing for a fixed set of well-known functions, we allow for any shape function that is learned automatically from data. These shape functions may be modeled, for example, as univariate neural networks or cubic splines. Similarly to symbolic regression, we can represent Schaars using an expression tree, as seen here on the left. And we also know that both GAMS and symbolic regression can be considered a special case of Schaars, so this is a kind of unifying formalism for both. And so, as we hinted before, not every closed form expression is transparent. It has to be compact enough to understand it, and Schaars inherit this issue. That means we need some criteria for building transparent Schaars. And currently used constraints in symbolic regression are often put on the number of terms or the depth of the expression tree. However, these constraints are not really grounded in how the model will be analyzed. So although they are correlated with the difficulty of understanding the model, they are not based on any assumptions how the model is actually understood. Therefore, it is unclear whether they capture how comprehensible the model is, and instead would like to take a different approach. So here we do not assume that the expression is meant to be understood immediately by looking at it. Instead, we assume that understanding it is performed by decomposing the expression into smaller building blocks and then understood from the ground up. So consider the following equation and its decomposition. This equation can be understood from the bottom. So we'll start with the simple univariate functions that can be readily understood by just looking at their graphs. And then we have multiplication of S2 of X2 and X3, which should also be pretty straightforward as both terms depend on different variables. So we know, for instance, that multiplying X3 by 2 will always make the product 2 times bigger, no matter the value of S2. The next step would be adding S1 of X1 to the previous terms. And that's also pretty understandable because if we increase S1 of X1 by any amount, the whole sum will always increase by the same amount, no matter what are the values of other variables. So this independence seems to be very important. And finally, the value of the whole expression is passed to S0, which once again, as a univariate function, can also be understood by looking at its graph. So when we come back to our challenge of defining some kind of constraints for Schaars, we see that to enable such understanding by decomposition, we can introduce two general rules for constructing transparent models. And these two rules can be treated as a sort of axioms for our rule-based transparency. So we have rule 1, which says that every univariate function is transparent. And if a model is transparent, composing with a univariate function keeps it transparent. We also introduce a second rule that says that if two models are transparent and have disjoint sets of arguments, then they can be combined using any binary arithmetic operations, and their transparency is preserved. And although it may seem that these rules are quite restrictive, it's interesting to know that 86% of physics equations from the Feynman symbolic regression database actually can be put in a form that satisfies these two rules. So this hints that maybe this class is expressive enough for what we want to do. So these two rules help us define a subset of Schaars that we called transparent Schaars. And apart from requiring that each binary operator is applied to functions with disjoint sets of variables, we've also included two other constraints to remove unnecessary redundancy and constrain the search space. So we don't want to directly compose shape functions with one another, and we also remove the numerical constants because these can be always absorbed into the shape functions. And the upshot is that not only these transparent Schaars can be understood by the composition, as we previously shown, but also their size is naturally constrained. So in particular with n variables, the depth of the expression tree is at most 2n, and the number of nodes is at most 4n minus 2. So we don't have to put any arbitrary threshold. They are naturally constrained just using these two simple rules. So far we have showed how Schaars generalize closed form expressions, and this allowed us to define this new notion of role-based transparency. However, it's interesting to now go back and represent some closed form expressions as transparent Schaars. And what do I mean by that? So consider the following physics equation. Understanding this equation may require a bit of effort due to complicated interactions between variables. However, we can rewrite it as the following Schaar, where the shape function S1 can be readily visualized. So we can now understand many important properties directly from its plot, and thus the whole equation also seems more straightforward than before because of this new representation. So now to show how Schaars can be used in practice, we implemented a simple version of Schaars based on genetic programming and with univariate neural networks as shape functions. This was mostly for illustrative purposes, and we expect much more efficient implementations in the future. So we wanted to test it on the following quite simple but still challenging problem. Given m grams of water in a liquid or solid form of a particular temperature, what would be the temperature of this water after heating with a certain amount of energy? So it seems like a simple problem with just 3 variables. However, when we apply just standard symbolic regression, we see that it actually doesn't perform that well. So here we can see different equations for different sizes. And we see that all of them fit the problem quite poorly. And if we look at longer equations, they're very difficult to understand, while still the fit not being very good. This also doesn't work with GAMs very well. So GAMs also seem to be incapable of fitting this problem. And not only they have a poor fit, but 2 of the 3 shape functions are very difficult to interpret because they are very jagged. So finally, we apply Schaars. And in the table, we can see that the vast amount of expression for the corresponding number of shape functions. And we can see that not only we have a perfect fit for the expression in the third row, but also if we look at the shape functions, they are very easily interpretable. So interpretable that we can actually analyze them further and extract important physical properties, such as specific heat capacity of water or heat of vaporization. And in this table, we can see that these values, extracted values, actually match closely with the ground truth. So I would like to end the presentation of this paper with a short discussion about the applications and future work that we envision. So first of all, Schaars not only makes symbolic regression more flexible and possibly even more interpretable, but also allow for the use of categorical variables, something that has not really been addressed in the symbolic regression community before. So this can prove useful when we investigate phenomena comprising different objects with some possibly unknown latent properties. In that setting, Schaars may naturally learn a shape function that differentiates between those objects and their properties. In general, as any transparent model, we think this is going to be applicable in high-stakes scenarios, such as risks prediction in healthcare or finance. However, we mainly envision its use in AI applications for scientific discovery. We believe that we need to add more flexibility to our models for AI for science to advance beyond the synthetic experiments based on simple physical equations, as it is often the case for symbolic regression. Transparent Schaars add this flexibility without compromising the comprehensibility. And in addition to it, AI for science is also likely to contain multiple scenarios where we have this adequate resources, time, and attention that can be spent on analyzing and understanding the models thoroughly from the ground up in a way that is facilitated by the rules we propose. Additionally, Schaars also provide a new convenient formalism for symbolic regression, which we believe can be leveraged either to come up with new transparency constraints or new optimization techniques. And finally, we hope this new kind of role-based transparency can inspire novel, more systematic notions of transparency grounded in the way the model is supposed to be analyzed and understood. So Schaars fit into an important area of explainable AI, or XAI, called transparent or white box models. So models that are interpretable by design or inherently understandable. Commonly, such models include symbolic regression, generalized additive models, linear regression decision trees, and finally, hopefully soon, shape arithmetic expressions. And as I discussed before, not every instantiation of these models would be considered transparent, but most people agree that at least subsets of these models are transparent. Now, we observe that all these models share an important feature. They all issue static predictions. The prediction is basically a single label. It's a real number in regression setting or a class in a classification settings. However, models can have more complex outputs. In particular, in time series forecasting, the output is a whole trajectory, a sequence of values, or even you can treat it as a real function in a continuous setting. For such model, it is not very clear which models are transparent and what it even means for forecasting models to be transparent. And these are the questions that we aim to address in our recently published paper, Towards Transparent Time Series Forecasting, authored by me, Tennyson, and Michaela, that we're going to present at this year's ICLR. And first of all, we have plenty of XAI techniques. So why do we want to move towards transparency? Let's consider the following problem: forecasting a tumor volume trajectory from patients' baseline covariates and drug dose. Such models may be crucial, for instance, for planning treatments. So standard XAI techniques, such as feature importance and case-based methods, may answer questions such as how important is a specific covariate for the prediction, or how similar is this instance to other instances in the dataset. But in reality, we might want to answer more meaningful questions about the model. So here we refer to questions from so-called XAI question bank, which was compiled by researchers by looking at what kind of questions are important for understanding models. And the researchers then grouped these questions into 10 distinct groups. So here we selected the 3 of them and the representative questions. So these are questions like, what if, with an example of what will happen to the model's prediction if a specific covariate changes, how to beat that, how should the covariates be modified to get different prediction, and how to still beat this, with an example of what range of drug dose values keeps the prediction the same. Okay, so we established that we want to create a forecasting model such that we can answer these questions. So what's the challenge? So if we look closer at the questions from the previous slide, all of them require some notion of understanding or measuring the change in the trajectory. And it is much more challenging in models than in models with single label output. Because when we have just a single label output, there's not much that can happen. If it's a real value, it can either increase, decrease, or remain constant. If it's a classification model, it can just change from one class to the other. However, if we have a whole trajectory, it can change in multiple ways. Like we can say it has much more degrees of freedom. And now, in fact, answering these kinds of questions with current XAI methods is actually not very helpful. And why? Because all of them represent something that we call bottom approach to trajectory comprehension. So now, what do we mean by bottom approach? So to illustrate what it means, we consider feature importance methods, which are probably the most commonly used methods in explainable AI. And although these methods have been extended to time series inputs, some of you may know Dynamask, developed by Jonathan from our lab, limited work has been done to extend them specifically to time series outputs. In fact, most of the algorithms are often agnostic to the type of the output. So often the values in insanity methods are just calculated independently for different prediction horizons. And this represents bottom-up approach to trajectory comprehension. It means that trajectory is understood by looking at its values at individual time points. So we could, for instance, use something like SHAP and get a figure like this, where we get the importance of 2 static features, alpha and beta, for the predicted trajectory at each time point separately. This allows us to answer questions such as, such as how important is the dose for the drug concentration are T equal 1.5 hours, right? And this may be sufficient, for instance, if we're interested in just 5 years survival rate, but this ultimately reduces the problem to static prediction. So in general, we argue that this strategy for trajectory understanding is not optimal in many scenarios. First of all, it is not a natural way for people to understand trajectories, as shown in research papers investigating how people understand graphs. And it is challenging to piece together how the trajectory changes from all the changes at the individual time points. So, and most importantly, often we want to comprehend the whole trajectory. So, for example, when administering a drug, we may be less interested in the concentration of the drug every few hours, but rather in understanding the entire curve, including properties like the peak plasma concentration and the time when it is achieved. So I hope I convinced you that answering the questions from the previous slide with the current bottom approaches may often be futile, since the notion of a different prediction based on individual time points may not be interpretable or too simplistic. So now, what's the alternative? So first we make the following observation. Humans tend to describe trajectories by referring to the trends and properties it exhibits rather than just the values it attains. So if we look at 3 simple examples of trajectory descriptions in natural language, we can observe the following. So let's take the first example. The GDP has been steadily increasing for the last 10 years. We have a description of a trend, the general shape, that the trajectory is increasing, and we have a certain property of this trend, like for the last 10 years. Another example from the last row, the tumor volume decreases, obtains a minimum after 6 months, and then increases. So we have a description of the general trend, decreases and then increases, and we have some property of this trend, that the minimum is at 6 months. So the top-down approach to trajectory comprehension, in contrast to the bottom-up, looks first at the general trend of the trajectory and then at the properties of the particular trend. And this is how we can achieve an interpretable model. Instead of tracking the individual values of the trajectory, as in bottom-up approaches, we track how the trends and properties of the trajectory change as we vary the input. And thus we can define a new notion of transparency that we'll call bi-level transparency, where on level 1, we want to understand how the trend, the general shape of the trajectory changes as we modify the input. And on the second level, we want to understand how the properties of the current trend, for instance, the minimum value, changes as we modify the input. So now that we have this conceptual framework with trends and properties, we would like to formalize it. So what exactly is a trend? What exactly is a property? We propose to formalize a trend using the notion of a composition, where a composition is in turn a sequence of motifs where each motif describes the current shape of the trajectory at a specific interval. So for instance, we can choose a set of 3 motifs, increasing, decreasing, and constant. And then we can divide the trajectory into a few segments. So each can be classified as being in one of these motifs throughout the interval. Thus, we can assign a sequence of motifs to this trajectory, and we will call it a composition. So now we map the trends to the compositions. And now what's nice about it is that we have the natural mapping from the properties of the trend. These can be represented by the transition points between the motifs. And now the choice of motifs is, of course, application dependent, and we describe a few possibilities in the paper, but a good starting point is something that we call dynamical motifs. So dynamical motifs encode the information about the first and second derivatives, and you can see there are 7 of them. The first 3 of them describe straight lines with either positive, negative, or 0 slope, and the next 4 describe strictly increasing or decreasing functions that are either strictly convex or strictly concave. What's nice about these 7 motifs is the transition points between them correspond to local minima, maxima, and inflection points. And these properties are actually crucial for function sketching, which is a common mathematical exercise whose task is exactly to understand the function. And these dynamical motifs are going to be essential when they describe a particular model adhering to our framework. But now, before I do that, I need to narrow the focus of our discussion a little bit. So everything I described refers to the output of a time series forecasting model. This is the focus of our work, and this is what makes it different from tasks such as classification and regression. However, time series models may take many types of inputs, including static features, information about the future, other exogenous time series, and everything up to this point was agnostic to the specific kind of input. But now to provide a clear exposition of our framework and demonstrate a practical limitation, we need to focus on settings where the inputs are just static features. This is still a very rich area, so because static features may include things like baseline covariates, types of action, dose and strength of treatments, initial conditions, or even a few initial observations. And we can find plenty of settings like these in medicine, pharmacology, time to event problems, and even dynamical systems. So now we'd like to present an example of a simple model adhering to our framework that we call TimeView. It consists of two parts, and a predictive model and a visualization tool. So to ensure that TimeView is bi-level transparent and to use dynamical motifs for it, we need to satisfy two things. So one, we need to understand the relation between the feature vector x and the composition of the predicted trajectory, and understand the relation between the feature vector x and the transition points of a given composition. So in particular, we need to carefully choose the hypothesis space for our trajectories, because it's important that for every predicted trajectory, we can uniquely assign a composition constructed from dynamical motifs, and that for every such trajectory, we can calculate this composition efficiently. Fortunately, there's a very natural choice, cubic splines. So cubic splines are a piecewise functions where each segment is defined by a different cubic polynomial. And they're very nice because we can very efficiently calculate what's the composition for each of the cubic polynomial parts, and then we can combine them into the composition for the whole trajectory. Another very nice property of cubic splines is that we can actually describe them using B-spline basis functions. So these are very special piecewise functions, which basically guarantee that every cubic spline can be expressed as a linear combinations of the B-spline basic functions. So in principle, we can describe every trajectory as just a list of coefficients or as a vector of coefficients of these different basis functions. So, and this leads to a very simple architecture where basically we take the static features, we encode them for a neural network into a latent vector that acts as the vector of coefficients of the B-spline basis functions. And then the predicted trajectory is fully determined by them, and is basically just the linear combinations of these basis functions. To train the model, we do a little bit of pre-processing. So the knots for, so the places where the different cubics connect are fixed for all the samples. So before we do the training, we need to choose what these knots are, and we designed a simple heuristic algorithm to do that. We basically define the basis, the B-spline basis function based on these knots. We evaluate them on the time points of interest from our data set, and we can combine them into these nice matrices in such a way that the training process is very simple, because after encoding the static features as these latent variables, the only thing we have to do is multiply by this matrix, and we get our predicted values at this individual time points. So the training and inference times are very quick, as the trajectory can be inferred in a single pass through the network. And as I mentioned, as the trajectory is uniquely described by a vector of coefficients, the composition extraction can also be performed analytically and very efficiently, just knowing the latent vector C. So finally, it's time to show you how TimeView can be visualized. So the interface consists of three parts. We can visualize the effect of perturbing one feature at a time using these colorful bands. And in left panel, we have a movable slider for each feature that changes the predicted trajectory in the center. The color on the band below the slider signifies the composition of the trajectory if the feature is in corresponding range. This allows us to understand how the trend of the trajectory changes as we change each feature. And this corresponds to level 1 of our bi-level transparency. To understand the properties of this trend, so level 2 of bi-level transparency, we choose any of the transition points in the central plot, and then we can analyze its position with respect to the chosen feature on the plot on the right. So it currently shows how the y-coordinate of the second transition point, which corresponds to local minimum, increases as the initial tumor volume increases. So we'll now demonstrate how we can answer many meaningful questions about our model using this interface. So consider the first question. Would the predicted tumor volume keep decreasing if we adjusted the treatment? This is a question on level 1 about the trend of the trajectory. The center plot shows that the current trajectory is decreasing, and the colorful band under the dosage slider shows the compositions for different drug dosages. And we can see that the trajectory is increasing for very low dosages. This is in color orange. For higher dosages, in blue, the trajectory is first decreasing and then increasing. And finally, for higher dosages in green and pink, correspond to decreasing trajectories. To answer the question, it is enough to check at which point the bands change the color. So if the drug's dose is kept above 0.46, the trajectory will keep decreasing. And then we can use the secondary plot, which shows how the y coordinate of the first transition point, which is the predicted initial volume here, changes as the provided feature initial tumor volume changes. So as expected, the plotted function is close to identity, and this is just a good sanity check to confirm that our model learned that one of the static features actually corresponds to the initial measurement. We can consider a different kind of questions. For instance, what feature changes will lower the minimum tumor volume? And here, this is a question on level 2 about the property of a particular trend. So let us consider a lower drug dosage where the trajectory first decreases and then increases. And we can observe that the minimum of the tumor volume corresponds to the y coordinate of the second transition point. So now we can use the tool on the right to plot how the minimum depends on the dosage or basically any other feature. And we can see here that the minimum volume decreases with the increased drug dosage. We can slightly switch this question, and instead of asking about the minimum tumor volume, we can ask how feature change and how would the feature impact the time this minimum is achieved. So now the only thing we have to do is we have to change which coordinate of the transition point we look at. So instead of looking at the y coordinate, we can now switch it to t coordinate. And now we can see how the time of the minimum depends on the dose of the drug or any of this feature for that matter. So previously I showed how we can visualize the model when we want to perturb or see the effect of one feature at a time, but we can also visualize the effect of changing two features at a time, of course. We can use these 2D plots, these 2D contour plots, where each color corresponds to a different composition, and now it is clear how changing the features influences the composition of the trajectory. Apart from visualization, of course, we compare time view to other kinds of models on variety of data sets. But what's important to take away from this is just that time view outperforms other transparent techniques, which are basically just transparent models such as counter decision trees adapted for time series forecasting, and achieves performance comparable to black box models. So now we believe that bi-level transparency and our mathematical framework can inspire future XIM methods. For instance, note that models adhering to our framework, like TimeView, provide additional output next to the standard forecasted trajectory, the current composition, and the coordinates of the transition points. Traditional XIA techniques for regression classification can now be applied to these additional outputs instead of individual trajectory points to gain more meaningful explanations. Thus, techniques such as feature importance methods, local surrogates, and counterfactual explanations can now be extended to time series forecasting settings. These, in turn, can open domains where the applicability of machine learning has been limited due to transparency concerns, including medicine, finance, and science. And that's everything I wanted to say. So I hope you found these papers interesting and enjoyed the presentations, and I'm more than happy to answer any questions you might have.
Now, though, I'd like to move to the second part of the session today, and that is our panel discussion. And I'm delighted to welcome three guests today. Our first guest is Dr. Ramon Hernandez, who's the Global Head of Development of Real-World Evidence at Sanofi. We're also delighted to welcome Dr. Sean Hayes, who is the Associate Director for AI and Machine Learning at Merck Co. And finally, but by no means least, we're delighted to welcome Dr. Richard Peck, who was the former Global Head of Clinical Pharmacology for Hoffmann La Roche and is now an Honorary Professor of Pharmacology and Therapeutics at Liverpool University and Associate Faculty at the Cambridge Centre for AI and Medicine. I'd like to invite our three panelists to kick off the discussion today just by maybe providing a very brief introduction beyond this about kind of their area of expertise and why and the area they're most focused on working in and why they're maybe so excited about this area. I'm not sure who would like to kick us off here, but
I think we should start
Richard, I
with
could
Richard, if you allow
you.
me. Yeah, maybe Richard, because the reason why Krzysztof is a PhD student in our lab is funding that was provided actually by Richard. Sorry, Fergus, to intervene.
Yeah, and I will emphasize again, Krzysztof, and to everybody else, I am very definitely not technical on any of this. So, you know, first of all, it's great to see the work you've done, I have to say that. And I think you're tackling a couple of areas that are extremely important for, I'm going to focus obviously on medicine and treatment and drug development and drug use within that, but and I will come back, Fergus, and I promise I will say a little bit about my specific interests. But I think there's no question that in medicine, both for the drug developers and the future prescribers, and I used to be a future prescriber as well, as a drug developer, for willingness to engage in AI, transparency is extremely important. And any work that is being done to further increase the ability to have transparent models is useful. And I'm not going to pretend I understand all the details of the first part, but at some point it would be kind of interesting to understand a bit more about how you can utilize some of that transparency to solve problems that we often have of trying to understand what really are the relationships between various parameters in a complex way, and undoubtedly generating complex equations for which we may have very little prior knowledge. But now, to get to my interest, and I actually want to move on to the time series thing. I mean, my interest, and Mihaela and others knows this very well, is understanding variability in drug response, which includes understanding variability in disease, because I want to move away from the current way in which treatments are used, which is essentially driven by population level data. And I want us to be able to understand how to make accurate, reliable predictions for individual effects. We still have to use population data to get there, but I am intrigued by what the potential might be for particularly the time series work to improve our ability to make individual level predictions of time courses. And I'm completely with you that time course is way more important than just a binary, yes, it'll be this, or no, it'll be, yes, it will get above this point, or no, it won't. No, the time course is way more useful. And when we first set this PhD up, one of the things that I was chatting to Mihaela about was how can we get better at using AI for relatively small data sets, such as you might have within an individual clinical trial or even an individual drug development program, where you don't have the luxury of tens of thousands of patients being treated. So, at some point, I would also like to come back to that question and explore that a little bit more with you. But again, I think there's some potentially very exciting stuff here. I think there's still a lot more we can discuss. I will stop there because I'm interested to hear what Ramon and Sean want to say, and obviously give time for the audience to ask questions. But again, congratulations. Great to see what you've been doing.
Thanks, Richard. Ramon, I don't know if you want to jump in next. I see you're off mute.
Yeah, no. First of all, congratulations, Krzysztof, because you did really a great presentation, and thank you, Richard, to frame the topic in such a wonderful way. I think that I concur 100% in every single sentence that you are saying, from the interest of increasing the transparency in terms of basically I'm speaking about clinical development, because I think that where really there is a big field of opportunities to introduce this kind of new approaches are in the development of our drugs, before even moving to the prescription of those drugs, before moving to the real world. Because if we were able to apply those principles, and of course also these inspirational papers and wrote by Mihaela and other colleagues about individualized treatment effect estimation. If we were able to move from this broad average effect in the population from the RCTs to estimate the individual effect of the different treatment based on the feature of the people that can benefit from this treatment, I think that definitely we will change this all RCTs back from the 20s, no? 1984, if I remember correctly. And I do, I think. So I think the question for me, which is really, really interesting, is exactly what you, Krzysztof, described in terms of the minimum dosage and also how other features can impact the determination of this minimum effect in terms of the treatment. And it will be good to explore that, how this can be applied in, for instance, in the phase 1 of the clinical studies, right, where by now the industry approached that in a very old fashion, no? To explore 100 or 1,000 of different dosage to get a final effect, which I think is totally archaic, so from all times. So I really congratulate Krzysztof for the approach, and I would like also to hear how that can be applied also in this specific problem, which is to know what is the best dosage, for instance, in oncology, back to the same topic that you are discussing, but not at that point, not related to the effect, but related to the effect of a drug, which is hypothetically developed for a specific treatment, and also to move from this average treatment that we have now to the RCT, which are very individualized impact.
Thank you, Ramon. Sean?
Yeah, hi. So I'm Sean Hayes. So I work for Merck, and I'm specifically sitting in our quantitative pharmacology and pharmacometrics department, where essentially we do pharmacological modeling, either pharmacokinetics or dynamics, to support either internal decision making. Do we advance programs to the next stage? Clinical trial design, and also we communicate with regulators. So I'll echo something that Richard said initially of, I'm interested in this because, any willingness to participate in AI, especially when you're talking about interfacing with regulators, and also, when we're providing decision-making support, it's typically for people who are, we're quantitative modelers, and then we're, advocating for decisions to people who are, biologists, clinicians, people who don't necessarily have deep quantitative expertise, even with our tools, which are, decades old at this point. So any willingness to interact with any AI technology, you have to be able to explain it. It has to be transparent. So that's this. I think a lot of this work speaks right to the heart of that. And I'll also say symbolic regression. I think I keep coming back to it as a important tool in from my experience, just because this task of learning. Learning in a transparent way what the kind of equations describing physical phenomena are. It's a very fundamental problem. It's essentially what we do when we're doing pharmacology modeling and a lot of other different things. And it's a very human-driven process right now, and it's often a very bias-driven process or time-consuming driven process. So finding ways to bring, I see it as a huge unmet need for AI/ML. So it's really, really cool seeing progress there and things. So I guess my current thoughts are we're really excited about applying these kinds of things and getting our toes into them. And the challenges are I see talks like this as really cool methods. It seems like there's a bunch of different things that people are trying. I'm curious, how does this stack up to either other symbolic regression methods? I think that the time series forecasting way seems like a very very, very different to other things that I've been exposed to so far. So it's very, very interesting. So how does that stack up with something like the neural ODE methodologies that are coming out and things? So that's it's really seems very, very creative, novel work, at least to me. Maybe other people have seen this. Was very, very interesting ways of tackling these things. So happy to hear more.
Awesome. Thank you, Sean. Krzysztof, I don't know if you want to comment on Sean's point, on Sean's question there to you, perhaps.
So sorry, the question to me, you're saying?
Yeah, it would be good, Krzysztof, you answer the challenges that our three esteemed panelists have put to you. Maybe you start with Sean, and then you go back to Ramon, and then you end up with Richard.
Oh, there were many challenges mentioned. I don't think I can conquer all of them. I'll maybe mention something about this personalization. So this was one of the motivations behind behind like TimeView and this general methodology, and the fact that we can see how this model gives different predictions for different static features. So effectively for different people, and this can be used in two ways. So I initially envisioned it as more for model development, where we have a ready model and then we want to investigate whether it is actually safe, whether it is predicting what we want to have. But there's also the other aspect, more application based, where we have already model and we want to use it in practice for a particular patient, but we want to see we want to see this all possibilities at the same time, just by looking at one instantiation of the interface, basically. Sean, if you could just summarize your question quickly, because I think I missed maybe what the exact question is.
The question was how this relates to neural ODEs. That's number one. So I think you should answer that. Yeah. But also another question that Sean put was, how do you take this to data? And you have taken this to data in your work, inclusively from data from Professor Jean-Baptiste Voyard, who is on this Zoom. So maybe you can answer both questions.
Yes, so of course there is a relationship to neural ODEs in a way that both of these are about time series forecasting. So the main difference, so in my paper, I kind of proposing a framework how to understand this kind of time series forecasting models. And the particular implementation when I use these cubic splines is just an instantiation that fits into this framework. It would be difficult to apply this framework to, let's say, neural ODEs, because in neural ODEs, we don't really have much control over how many trends we have, or like how quickly this trend changes and so on. Whereas with cubic splines, the control is very easy. We just say how many knots we allow, and then we know that these compositions are somewhat restricted. So we know that we don't suddenly have trajectory that change their shape, like 100 times in a very limited time. So it might be that if you try to explain the predictions of neural ODEs using this method, you would get the result when the composition changes by every little change in any of the features. So it might be very difficult. If you put like some additional constraints, if you make sure that you can actually and there's an issue of actually calculating this composition. So with cubic splines, I can calculate them analytically very quickly. With neural ODEs, I would need to go through the entire trajectory and actually approximate how the slope changes, and very numerically calculate what's the actual composition. And that also just takes much more time and is less accurate.
Just to add on to that, this should be an easy one to answer. But so for pharmacology, as you alluded to, we have specific properties that we're usually particularly interested in, like area under the curve or time at maximum concentration. How amenable would this methodology be to focusing to like specific quality, like I'd say like user specified or custom properties like those?
Yeah. So when when I talk about trends and properties in the framework more conceptually, I mean all kinds of property that makes sense. So I of course propose like minimum maximum inflection points because they are quite simple. They are easy to formalize, but there is nothing forbidding from having just one more property. Instead of looking transition point, I can choose an additional property, which is the area under the curve or something else. So it definitely fits into the framework, and it fits into this top-down approach to trajectory comprehension, when you don't care about the individual time points, but you care about this more holistic understanding. Yeah, definitely.
Excellent. Thank you.
Can you say how you take this to data, Krzysztof?
Yes.
Because I think that is very important, and the work that you have done with real pharmacology data, and one of the collaborators we had that provided you such data is again Jean-Baptiste, who is on this call.
Yes, and I saw questions from Jean-Baptiste as well about this. I'll try to answer them as well. So it's true that the real data is quite noisy, which makes this quite challenging to fit. Now, initially, I thought there would be like nothing special about like the implementation I have, because once again, it was mostly for illustrative purposes. But actually, a very interesting outcome has appeared that because I use a neural network to kind of fit these trajectories, and these trajectories are supposed to be this quite smooth cubic splines, there is this implicit bias that makes these trajectories change quite slowly, which means that actually some kind of like context is added to this to fit these curves. So basically, if I just took for instance took all the data and just fitted a cubic spline, and I did it for each of the samples, I might get a very different fits. They would have a very different composition. They would look very different. But because I'm fitting all of them at the same time in this like end-to-end fashion, they seem to vary smoothly when I change the features, which I think is like much more realistic expectation than the composition suddenly changing if you just change it very slightly. So there is not like any inherent reason why this model would be, you know, better with noise. But then when you actually test it, there's this like implicit bias kind of things, which makes it maybe more applicable to noisy settings. And also there was questions about scarce data. I treat the question about noise and scarce data kind of similarly. Like these are both like data issues, and this, you know, this implicit smoothness bias once again may be a little bit helpful in that case. But once again, like the time view is like just specific implementation. There are probably many better implementations that fit the general framework that, you know, I look forward to exploring as well.
Thanks, Krzysztof. It was interesting to hear Sean and Richard, you both touch on kind of one of the key challenges being the kind of interpretability and transparency when you're looking to actually take some of these approaches from the machine learning community and think about translating them to actually impact the work that you're doing. Are there any other challenges you think that are maybe preventing more adoption, or some of the techniques that are being developed maybe more by our community actually having impact and impacting these areas? Is it even more transparency? Is it more of a translational kind of issue, or kind of another fundamental technical type point? Be really interested to hear your thoughts on this.
I certainly have them. I don't know if Dr. Richard is starting to say anything. Yeah, so I mean, the biggest challenge I think is actually a little bit more operational than it is technical, where you know, any you know, company like Merck or anywhere we're actively developing drugs, you know, the organization, when to invest in doing the current work of developing drugs versus, you know, any kind of methodological improvements, you know, that's historically challenging. So that's, I think, that's a big one, often because there can be a big gap between, you know, the kinds of papers, you know, Mihaila's lab, I've read lots of, you know, really exciting, interesting technical papers, and then, you know, the work from, okay, how do I get this into a form where I can make a case about this to even, you know, my quantitative colleagues who are outside of the machine learning space, where they're, you know, they're familiar with some tools, but they're not immediately going to grasp how this could be used, or, you know, get the case. So essentially, I need to do work to make a case for it. So, I mean, in that sense, sort of examples that are closer to, you know, our familiar applications, which is, you know, it's hard, requires collaboration. Those are, you know, those are worth their weight in gold alongside like robust benchmarking papers. You know, I light up when I see like a paper that's sort of robustly done a benchmark. If there's a figure that I can pull out and say, you know, this is the right method for the job, this is how it goes, you know, I can throw it into a deck and, you know, be able to sell it to colleagues. You know, that's that takes things a long way. But I mean, yeah, the operational thing is just hard. But yeah, those are the big things that I think about.
Thanks, Sean. Richard or Ramon, is there anything you'd like to also comment on and hear and add?
Certainly I mean, I think for medicine in general, and drug development as a case within that, there is a huge conservatism. You know, people stick with what they know and what they're familiar with and comfortable with. And anything new is going to take some time to come through, and that's particularly true if it's mathematical, to build on Sean's point that, you know, often you're sort of mathematically minded people trying to talk to people like me for whom mathematics is, oh my God. So there's you know, Mihail's not going to like what I'm about to say, which is that sometimes there's a need for patience. And we just have to accept it's going to take a while. I mean, a technique that Sean, I'm sure, uses regularly, the whole PK/PD modeling, you know, is now routine. It was first really developed in the late 1970s. And it probably took until the 2000s when the regulators started to say we want to see it, for it actually to become a fairly deeply embedded part of drug development. And it's still not part of clinical use. So it gives you some idea.
Richard, I don't like that. You know, I'm impatient.
Yeah, I know. Well, I knew you weren't going to like what I was going to say. And one of the things that I think some of us, people like me and Ramon and Sean, I hope can help with is to try to accelerate the whole process by increasing familiarity. But there'll be no substitute. You know, the work that's being done, there's no substitute for getting the examples out there, you know, showing the medical community what not just what the detail is, but what you can do with it, why it matters. There's a tremendous clinical pharmacologist who talks about communication, and he says, I don't want to hear about properties. I want to hear about what the impact is. Don't tell me the car has a 300 horsepower engine. Tell me it can get to 60 miles an hour or 100 kilometers per hour in 4 seconds. Okay, so, you know, when communicating to the medical world, really tell me about the benefit, not the features. And you'll drive faster uptake.
So to add to that, you brought up, I think, another important point is, I mean, you know, regulator uptake is another, like there's sort of the triangle of, you know, academia, there's things that, you know, and I have seen a little bit more from FDA of, you know, their interest in some of the AI/ML stuff. And I think nothing gets people in my department to pay attention more than seeing that regulators are thinking about it or even asking for it. So I mean, bringing them and, you know, socializing it with them whenever we try to do something new, we have to socialize it with them. So getting them familiar, making the case to the regulators. I mean, that's, you know, that if you could do that ahead of even, you know, the pharma people, you know, we follow what they ask for. So.
Yeah, no, fully agree on everything that you are saying. But the regulators by now, by definition, they are quite conservative, and we need to understand that, because the responsibility of what they were doing, you know, the criticism is basically inherent to the job that they are doing, looking at safety mainly, of the drug. So what they have always this adverse reaction, and it's more on us, on as you said, in this area of having together academia, regulators, and perhaps pharma, where we can move forward in introducing new approaches and new methodologies that they really need to be done. No doubt on that.
Krzysztof, I know you had some questions for our panelists. Would you like to, in the time we've got remaining, would you like to ask maybe one of your questions? Perhaps starting off with a question for Ramon.
So I'll choose maybe one question, because this topic just came up about pharmacology, PK/PD modeling, and so on. So I was just wondering, usually right now, as far as I understand, these PK/PD models basically consist of closed form ordinary differential equations. And I'm just wondering, do you think they could be in future replaced by other, possibly more flexible machine learning models? And like, what would be the main challenge in the transition? So now I'm not talking about how do we persuade, but like more, let's say, technically, what these models, what kind of properties would they need to have for the, let's say, regulators to say, oh, actually, yeah, this is as just good as ODEs, and we can accept them. Do you have some thoughts about that?
Sean's probably the expert. I might let him go first.
Yeah, so I mean, so sort of what we were talking about. I mean, you hypothetically, you could make any case to the regulators if it, you know, works well enough and you have enough time. I'd say, you know, I mean, you'd need head-to-head compare. Essentially, you need to show that, you know, can it make the right predictions? Something that we think a lot about internally when we're doing these benchmarking is, you know, can it extrapolate? Because I mean, in interpolation, you know, if you're sort of within a regime where you have data, that's, you know, there's plenty of methods to handle that, right? Like you really don't need anything fancy with that. But what we care about the most is, okay, I have data on this set of doses in patients. Is this the right dose? If I am sort of looking ahead to other regimes, I need to make decisions based on that kind of extrapolation. And the tools that we have, we have an ODE that's constrained to known biology. They're specifically very good at doing that. Whereas, like a recurrent neural network or a lot of the sort of interpolative machine learning methods, they completely fall flat when you try that. So that property is the big one that we test for, and I think that's what got us excited about neural ODEs currently. You're starting to have methods where you can build that in. So it being interpretable and transparent is a really big deal. Although I think even that's potentially surmountable. Like if you can demonstrate over enough time and with enough data, potentially that's surmountable. But yeah, I'd say, currently, the methods that we have work very well. I think the biggest issue would more be that the time that they take to implement and everything like that. So if you're trying to make a case to FDA, you have to show that they work as well as the current methods. And if they save time, I don't think FDA cares as much about it saving drug development time versus being kind of correct and accurate and everything.
Oh, thank you so much for all of your answers. I want to now take a couple of questions from the audience, and then I see we don't have too much time left, and so then we'll wrap up. So. I think we've got a question from Tao in the audience. Tao, do you want to unmute yourself and ask your question? If not, I can read up your question for you. Maybe I'll read it out. So this was a question for Krzysztof related to both talks, and the question was, what if you get multiple or many plausible solutions when the training data is scarce? So, Krzysztof, if you want to comment on this kind of multiple solutions question.
Yeah, so I tried to a little bit address it earlier. So basically, let's maybe start with time view. So basically, of course, if you have less data, it's the fit is going to be worse. But because we have this implicit bias coming from or this different regularization and choosing a quite not very restricted, but a little bit restricted hypothesis space of these cubic splines, hopefully they're a little bit more robust to basically to scarce data. When it comes to shares, so it is possible to have two different solutions to the same data set. They can be different solution because there are like inherently different equations, or they may be the same equation but just represented in two different ways. We tried our best to make sure that the second bit doesn't happen, so that we try to in the definition of transparent shares, we try to remove as much redundancy as it was possible. Still, it is possible to find some edge cases when you would have two different representations and they would both fit the definitions and they would describe exactly the same data set, but hopefully we did our best. For the first case, when these are two different equations where they fit the equation equally well, I don't think I have a satisfying answer for now how to deal with this scenario.
No, thanks, Krzysztof. Finally, I'd just like, Jean-Baptiste, did you have any kind of quick comment or quick question you'd like to make on anything we've discussed today? I saw you had a couple of questions in the chat, so just wanted to invite you very briefly to comment or ask a question.
Thanks, Fergus. Krzysztof already answered my question about noise. The problem is that we always have noise, and it's really a problem in pharmacology. We have a lot of noise, a lot of intra-individual variability, not always explained by features that are accessible. And probably in the future, Krzysztof, if you could add some uncertainty in your prediction due to randomness, or I mean to features that we don't have, it will be fantastic. But I really enjoy the work that you present today. Anyway, thanks.
Yeah, I couldn't agree more. Like, uncertainty seems like a very natural, very important next step for this kind of work. Yes.
Awesome. Thank you so much, Jean-Baptiste. I think that just about wraps up today's session. I'd like to thank our three panelists, Richard, Ramon, and Sean, for their time today, and what I certainly found a really, really interesting discussion on a lot of the topics today. And I'd also like to thank Krzysztof for his talks today. If you have any questions related to his talk that didn't get answered or that you still have, do post them in the Slack channel, and I'm sure Krzysztof will be happy to keep chatting about his work afterwards. I'd like to say, just very briefly once again, mention the summer school that's being run this summer by the Cambridge Centre for AI and Medicine, that the summer school registration is now open, so do sign up now if you're interested. And then say that our next Inspiration Exchange session will be on the 13th of May, looking at causality and causal deep learning. Thank you once again, everybody, for joining, and in particular, thanks to our presenters and panelists, Krzysztof, Richard, Ramon, and Sean. Thank you so much, and enjoy the rest of your day, everybody, and look forward to seeing you for our next session soon.